मा विद्विषावहै ॐ शान्ति शान्ति शान्तिः।
In the last class, we saw a number of applications of finite element analysis. We saw really the breadth of applications. We saw a number of case studies from different fields, and I am sure that you are all convinced that this is a very good technique which can be applied to a lot of practical problems. From now on, we will study some of the basis or theoretical basis of finite element analysis. You may have to have background in various fields in order to understand exactly how this technique works, but as far as possible in this course we will see to it that all these things are covered and the course is completely self-contained. We stopped with the definition of stiffness. We said that it is easy to understand what is stiffness as far as the spring is concerned, but how do you define the stiffness for other components? We considered that if there is a force P that is acting on a spring, and if this displacement at this point is u, then we said that it is possible to define a term called stiffness K such that P is equal to Ku. Now, the question is, how am I going to extend this concept to other components or other bodies which are not necessarily nice springs like this? As a first case, let us consider a simple bar, and let us say that I apply a force P. Can I talk something as stiffness for this particular bar? Is it possible that we can define it? Yes. How do you define it? Maybe all of you are familiar with it. We know what is the relationship between stress and strain, right? What is, in a very elementary level, you would have defined stress as P by A, where A is the area of this particular bar. Okay, so P by A is equal to E into change in length. What is change in length in this case? Say for example, no, as far as the strain is concerned, what is change in length by original length? Okay, that is how you would have defined. So let me call this as the change in length as u, in a similar fashion as we say that the displacement of the spring is u, okay, divided by L. Now it's very simple to now say that P is equal to AE divided by L into u, right? AE divided by L into u. Now compare this and this, it's quite clear. I can call AE by L as the stiffness of the bar. So stiffness straight away is not a concept which is restricted only to a spring, but can be extended to, say for example, a bar. We are going to extend this for all other types of components as well. Now let us look at another problem. Let us see whether we can extend this kind of concept to a problem where, a simple case, very simple problem, where I have a P force that is acting on a bar whose, for example, cross sections or say A1 and A2. Now, this poses slightly more difficulty when compared to this problem, or it is slightly more difficult. Now, you can of course looking at it immediately say that, sir, it is made up of 2 bars, right, it is made up of 2 bars. So, I can say that why not you consider it as 2 bars. Once I start considering it as 2 bars, you come into the realm of discretizing this particular piece. You have discretized it into 2 bars. Now on, we take over, or we come into the realm of finite elements. Yes, that is a nice answer, but there is a small problem. What is the problem? Here again, like this case, we had stiffness to be only one number, AE by L, okay? Because one end was fixed. It was nice to me to say that the displacement is considered only at the bottom of the bar, and we arrived at this point. On the other hand, look at this. It is not like that. I have now 2 bars. Okay? If you look at these 2 bars which are joined at this point, okay, then this point starts moving, this point also starts moving. Okay? One end is not fixed. Easy to handle, of course, but slightly more complex than this. You can look at another problem where there are more number of bars, right. Now, there is a technique to handle this. In order to use that technique, first let us define what is called as a bar element. What is a bar element? Let us take an element which I now started calling this as an element. Let me take that element and put it out. Immediately you see that there are 2 guys sitting on either side which are called as nodes. So, let me call those nodes as say I and j, a very generic term, say I and j, correct. Now, let me define or determine the stiffness matrix. Note this, we are now going to define stiffness matrix of this particular bar which are defined by these nodes I and j. Of course, what is also important is the area, let me call this as A, area of this bar, as well as the length, this length, which I would call as L, and of course the Young's modulus, which I would call as E. Right? Okay. Now let us start with what we know. In this bar, let me apply a displacement, okay, which I call as say Ui, and fix j, fix j. Now, let me call the force that is required to cause this displacement as Fi. From my previous result, I know what is Fi. What is Fi? Ae by L into Ui. Obviously, when I fix this j is going to take a reaction, or in other words, there is also a force that is acting at j. Let me call this as Fj. From my elementary strength of materials, I know that Fj is a reaction, and that it is, what is that? It is opposite to Fi and of equal magnitude. That is right. So, Fj is equal to minus Fi. That is the first step. Now, let me again repeat this with j free, or applying a displacement of uj and fixing I. what is that I am going to do? I am now going to release this guy and say that let j move from the original position by an amount uj, and let me fix this position. Now, in this situation, what happens to fj? That is straightforward, and that happens to be ae by L into uj. And now what happens to my Fi? That is minus of Fj, or in other words, that is minus Ae by L into Uj. Is that clear? Now, coming back to my problem here, this particular bar is now has two nodes and is in a position where both the nodes would start displacing, or in other words, ui and uj exist for this element. Since I have derived in a very simple fashion what is fi and fj when one or the other are fixed, okay, it is possible for me to straight away get to a situation where both ui and uj exist. It is nothing but the superposition of these two results. So, when both ui and uj exist, I can say that fi is equal to ae by L into ui minus uj. Is that clear? And what happens to fj? Fj is equal to ae by L into minus ui plus uj. Is that clear? Okay. Now, this can be expressed in a matrix form. What do I mean by that? I can express this as ae by L into 1 minus 1 minus 1 and 1 multiplied by ui uj is equal to fi fj. Now, look at this particular equation quite closely. You can immediately recognize, what is that you can recognize? You can recognize that there is a force on one side and there is a displacement on the other side. So, in other words, this is a relationship between force and displacement, and that relationship has been brought about by this particular matrix. Is that clear? Okay. Now, comparing that equation with my first equation here, where it is P is equal to Ku for a simple spring, where I called K to be stiffness, and similarly there is a relationship between force and displacement. Okay. I can call that matrix which I derived now to be what is called as the stiffness matrix. Okay. So, that is the stiffness matrix. Now, let us understand what the stiffness matrix means. In other words, can I extend the concept of stiffness, the physical behavior or the physical understanding of stiffness what I have for a spring, to the stiffness matrix which we derived? In other words, if I had asked you to define stiffness and not write down an equation, you would have said that stiffness is equal to force per unit displacement. There was no problem because there is only one place where force is applied and one place where the displacement happens to be there. But what about in this situation? how do you now define here, or how do you physically get a picture of what the stiffness matrix is? Right? That is the question. How do you define it? Can someone tell that? Or in other words, I would call this as say K11, K12, K21 and K22, right? Of course along with AE by L. In other words, the same matrix can be written for us to interpret as K11, K12, K21, K22, that multiplied by U, say U1 and U2, where I and j's I have just replaced it by U1 and U2. If you want, you can keep this as I and j itself, so that if you are getting confused, you can say keep it as I and j itself. Now, in other words, my question is, what does K11 indicate? What is the physical meaning of K11? What does K12 indicate, and so on? Because here I said K indicates just force per unit displacement. In order to understand that, in order to give you a clue, let me say that I apply a unit displacement. Here it's force per unit displacement. Keeping that spirit, let me say that Ui is equal to 1, and let me fix the other side, Uj is equal to 0. Okay? And then look at the complete equation now. What is that on the other side? Fi and Fj. What does the first equation indicate? First equation, K11 is equal to Fi, right? And what does K21 indicate now? K21 is what? Right, Fj. Is that clear? Okay. Now can someone give me an interpretation of what is K11 and what is K21? One of you. Yeah. So it is nothing but
K11 is the stiffness of the first node of the first element.
Yeah, in other words, just to repeat that, what it means is K11 is the force that happens to be present at I, or the force to be applied at I, in order to have, note that, unit displacement at I and 0 displacement at j, right? And K21 is the force that is required to be applied at j in order to have a unit displacement at 1 and 0 displacement at j. The same thing, same logic can be repeated for j as well. You can put this as 0 and this as 1. You can again interpret this Kij. So in other words, I can have a physical interpretation of Kij's, which are entries here. K I is equal to 1, j is equal to 1, it becomes K11, I is equal to 2, j is equal to 1, it becomes K21, and so on. So I can have physical interpretation for Kij. What is the physical interpretation? What does Kij indicate? It is the force that has to be applied at j in order to keep, is that, no, look at this and tell me. See, K21 means it is, what is the displacement I have applied for I? It is unit displacement. So if I have to apply a unit displacement at 1, okay, then I can get, and a 0 displacement at j, then K21 is obtained from Fj. So if there is a unit displacement at j, okay, then Kij indicates the force that has to sit at I, right. So, it is the force that is required to make or to give a unit displacement at j, okay, and the force being measured at I, the force that is required at I for a unit displacement of j. So, that is a physical, simple physical interpretation. Yeah, of course, 0 displacement at I. Force that is required to be present at I for a unit displacement at j, 0 displacement at I. Now, let us look at this matrix closely. What are the other things that you see in this matrix? What are the other things that you see in this matrix? Symmetric, very good. So, this matrix is a symmetric matrix. Okay. It is not necessary that every matrix that we are going to come across is symmetric matrix, but this particular matrix, because we are just dealing with a linear elastic problem, this matrix happens to be a symmetric matrix. Very rarely do we come across matrices which are not symmetric, okay, and in this course most of the problems, except when we go to contact, we will only be dealing with symmetric matrices. Some of the large deformation problems have, of course, non-symmetric matrices. Let us not worry about it, but as you correctly said, the next thing that you observe is that this matrix is a symmetric matrix. Okay. Now, it is very simple now to understand that I can have, say, 2 bars which are here, or 2 sections in a bar, to have different A's, different E's and different L's, right. So, the only thing is that A, E and L would change. It would become A1, E1, L1, A2, E2, L2 and so on. Okay. Now, let us see how we can determine a composite or an assembled matrix of a bar which looks like this. Okay. In other words, this particular bar which we considered as I and j, okay, have what are called as how many degrees of freedom? 2 degrees of freedom. Or in other words, I and j, whose displacements are ui and uj, give the freedom for this bar to be displaced, okay, in the x direction. So, there are 2 degrees of freedom, or in other words, if you consider each node, there is 1 degree of freedom. What do I mean by degree of freedom? It means that this particular node I can be displaced only in the x direction and j can be displaced in the x direction. So, as an element, this has 2 degrees of freedom, 1 degree of freedom per node. Is that clear? Okay. Now, let us see how this concept can be applied to a composite bar and how assembly can be done, so that I get a composite stiffness of this bar. For that, the first thing I have to do is to determine the stiffness of individual bar. But before that, I have already done one job. What is it that I have done? I have already discretized this particular component into 2 elements. I did it by looking at it and seeing that there is a change in A, change in E and so on, if it happens to be there, and so on. And so, I have used that knowledge in order to discretize it. But there are a lot of other considerations when I discretize it, but that we will see as we go on. But right now, it is important to understand that discretization is very important and can depend upon a number of factors, one factor being a nice physical picture or an engineering sense, and that is what has helped me to discretize it. Let me now call this as element 1, and let me call this as element 2, and let me not right now worry about fixing this particular node. Okay, let me call that node as say 1, 2 and 3. Right? Is that clear? Now, let me call A1, this is of course say L1, let me give some lengths to it. Let me say that it is L1, and this length to be say L2. Just to generalize this problem, let me call the Young's modulus to be E1 of this bar and this to be E2. Is that clear? Okay. Since AE by L comes up as a unit, let me define K1 to be A1 E1 by L1 and K2 to be A2 E2 by L2. K1 is equal to A1 E1 by L1 and K2 to be A2 E2 by L2. Is that clear? Okay. Now, I can do what I can do is to write down the stiffnesses of individual elements and look at this kind of assembly, okay, for individual elements. Or in other words, how does this equation looks like? How does it look like for the first element? I can change that here itself. So how does it look like? It will be K1 for the first element, K1 minus K1, right, minus K1, K2 does not come here. We are only looking at the first element, minus K1 and again K1. Is that clear? Okay. Now, what happens to I and j now? What happens to I and j? U1 and U2. What happens to Fi and Fj? And that happens to be F1 and F2. Okay, I am not worried about what are the values of F1, how it looks like and so on. Just I am repeating it for this particular element. Is that clear? Any questions? Right? Now, I and j was a generic indices. Now, I have replaced it with the actual index. Now, let us now look at the second element. The second element can also be written in the same fashion. I will do it in the same matrix, or maybe we will write it separately so that things become clear. What do I get? Instead of now K1, K2. So, K2 minus K2 minus K2 and K2. Instead of now 1 and 2, what are our i's and j's? 2 and U2 and U3. Is that clear? Okay. And what happens to this guy here? F2 and F3. Is that clear? F2 and F3. Now, I have to assemble them. please bear in mind what are the steps that we are doing. We discretized it, first step. I will write it down at the end of this exercise, but nevertheless as we go along, please bear in mind what we are trying to do. We discretized it in terms of what we called as elements. In this case, the behavior is bar. We will come to what is behavior in a minute, but in this case, we call this as bar element, so we discretized it. The next step is we wrote down the stiffnesses. Okay, that is the next step. We wrote down the stiffnesses of individual elements. The third step is I have to assemble them. Okay, how am I going to assemble, or what does this term assemble mean? In order to assemble them, let us see as if, or let us imagine that we are building this bar. Let us not worry about the actual manufacturing process, it may be a turning process, let us not worry about that. We will assemble them as if first I will put this and later put that. In fact, it may well turn out to be a welding process because E1 and E2 are different. Okay, we may imagine that they are welded together. So first I take this piece, the first element, okay, put it there and identify these guys, these nodes there. Okay, let us imagine that that's what happens. Since I have already identified a node at 3, okay, so it's imperative that it also has a displacement u3. Let's say that it has a displacement u3, though more importantly this element does not support any force there. In other words, if I apply a force here, the force happens to be in the air, and this particular element does not support a force. In other words, there is no stiffness. See, when can you apply a force? Only when there is a resistance to it. Okay, or in other words, there is a stiffness to it, stiffness to the body on which you are applying. Now, since it's in vacuum, let's imagine that, let's not worry about anything else. So I can't put a force at that place, right? Or in other words, even if I put a force, there is no resistance due to this bar. So in other words, if I have to now expand U1 as U1, U2 and U3, okay, how will my stiffness matrix look like from our physical understanding of K? Let us see how it would look like. So I will have K1 no doubt, I will have minus K1, these two guys are for U1 and U2, and what will happen to my third term there? Very good, because you may imagine or remember our Kij definition. So here I will have minus K1 and then followed by K1, 0, 0, 0, 0. That is very good. Now let me go and put the other element here. Build them together, or in other words, weld them together. As soon as I do that, okay, this force what we have mentioned here will of course be supported. Let us not worry about that right now, but now the process is quite clear, and hence some of the zeros are now going to be replaced by the stiffness we are giving by introducing the next element, which means that I will have K2 coming to the aid of the first element. So K1 plus K2 minus K2 minus K2. Please note that this is the last term, okay, in the matrix, that is in the second row, and 2, 3 and K2. One other thing that you had not noticed in the last stiffness, when I said that, you just said symmetric, I'll look at it, but you have not noticed one very important thing in the stiffness matrix, which I will come to in a minute. But what is important here is that we have assembled the matrix. Okay. First thing is that look at the matrix size. Now there are 3 nodes and there is a 3 by 3 stiffness matrix and there are u1, u2, u3 that are not known, right. And what is the right hand side? What is the right hand side? Correct. So it is F1, F2 and F3. Remember that they are nothing but the forces that can be applied. It is not necessary that they should exist, but that can be applied to 1, 2 and 3. So this is the complete equation which I am interested in after assembling. So what is my next step? I have to apply what is called as boundary condition. Okay, I have to apply what is called as boundary condition. But before we go to boundary condition, let us look at this matrix closely and observe one more point. Again, physically, there is a lot of mathematical implications to it. At this stage, let us not worry about the mathematical implications, but physically let us look at it and see whether we know why it happens to be in this fashion. Look at that matrix. You will see that there are some positive terms and negative terms. Okay, K1 of course is positive, K2 of course is positive. So there are some positive terms and there are some negative terms. See that there is no negative term in the diagonals. All the diagonal terms happens to be positive. Apart from that, you also see one more thing. What is that you see? Zeros. So there are positive terms, negative terms as well as some zeros. And it is very clear that the diagonal terms are positive. Off diagonal terms, there are negative terms as well as zero terms. In this particular problem, there are negative terms as well as there are zero terms. The question is it that these terms that are sitting in the diagonals are positive only for this problem, it happens to be positive, or is it by design or it is by chance? Is it that it is positive only for this problem or for any other problem? Right? Is the question clear? Okay. What do you think will be the answer? So in order to, 1 minute, let me give you a clue. In order to answer that question, let us follow the same logic by applying say unit displacement at say for example 1 and then 0 displacements and so on. So now you can see or you can say whether this is positive by design or not by chance. Let us look at my first equation, say K1, say U1, even not a unit displacement, at least U1 is equal to F1. So U1 is equal to F1 by K1 obviously, right. U1 is equal to F1 by K1. What does this tell? If I apply a force F1, okay, then U1 would follow the force in the same direction as we know, as long as K1 is positive, right. So if I apply a force, I know that the displacement has to be in the same direction, it can't be in the opposite direction. So that particular condition is satisfied as long as K1 is positive. On the other hand, if K1 happens to be negative, what happens? Say for example, I take this bar, right, and then I start applying a force here. It will move in this direction if K1 is negative. That is not possible. Okay, the bar has to move in the same direction. So what does it indicate? It indicates that K1 has to be positive. And the next thing is that, is it clear? No? Yeah, just that is a very simple thing. On the other hand, can K1 be 0? Then U1 becomes infinity. So, necessarily these diagonal terms have to be positive. In other words, okay, we will come to a much larger condition of positive definiteness of stiffness matrices later. Let us not worry about it, because we have lot to learn from the physics of the problem before we go into the mathematics of the problem. I will not define all those things right now. Okay. Ultimately, we will come to them. Right. So, what is my next step? What is my next step? What do you think is the next step? Boundary condition. Very good. So, what is the boundary condition of this problem? This problem states that one is fixed and that a force is applied at this point, and that's a secondary thing. We will come to that later. But first thing is that u1 is fixed. Now, please note one thing carefully, that when I say boundary condition and say u1 is fixed, I just state that u1 is known. It does not mean, many students make a mistake that boundary condition means u1 is equal to 0. Okay, a particular degree of freedom u1 or whatever be the degree of freedom, that happens to be 0. Not necessary. It just means that the displacement for that degree of freedom is stated. In this problem, it is stated to be 0. Suppose in another problem I say that this displacement is 0.5 mm, that is also a boundary condition. Okay, boundary condition simply means in this particular problem displacement happens to be 0. Now, what are the types of boundary conditions, and what are the ways in which to express them? All these things we will see as we go along, but for this particular problem it is important to understand that the displacement happens to be a boundary condition, okay, and that displacement happens to be 0. Why I am stating this point is because a same configuration, as far as geometry is concerned, the same configuration can be looked at as a beam as well. The only thing is, if I now apply a force in this direction, it is no more a bar, a beam. It becomes a beam, which means that it can bend. A bar can take only axial loads, from strength of materials. Okay. On the other hand, a beam can take a bending load. Is that clear? Now, again I have different type of displacements, okay, a displacement which looks something like this, and I have different types of boundary condition. Now, what are the boundary conditions? Now, look at the question, what are the boundary conditions? Now, in the previous case for bar we defined what is the boundary condition, there is only one. Now, we just modify the problem and say that what are the boundary conditions? Displacement and rotation, that is right. So, displacement as well as rotation, both of them are specified at that place. So, in other words, the same node or the same position, same point is specified in a slightly different fashion, so geometry happens to be the same. Is that clear? But why is this difference? That is because of the governing differential equation for these two problems. They happen to be different. Okay? But before we go further, before we go to that point, let us now worry only about this problem and get a complete physical picture of finite element analysis. So, we will continue with this. So, as you correctly said, u1 is specified, so and u1 happens to be 0. Okay. So, how many unknowns are there now? 2 unknowns. So, u2 and u3, and u1 is already known and happens to be 0. Since u1 is equal to 0, I eliminate these two lines, or in other words, I eliminate that row and the column, okay, and restrict my attention to this particular piece. Now, I know something else also in this equation. What is it that I know? What is it that I know in this equation? F3, correct. So I know that F3 happens to be the applied force P, and what happens to F2? Do I know it or I don't know it? Is it that we don't know? Note that carefully. This is a mistake many students make. No. No, please note very carefully. Look at the problem again. Look at this problem again. Look at this problem. Look at this. Now, where is that node? Node is sitting here. It's nice that you have made that answer, because this is usually the confusion. Please note that what we are doing here is to put down the external forces that are applied. We are not worried about the corresponding internal forces that are developed. Okay, we are looking at the external forces. These are the external forces. Please do not get confused between that and the internal forces which are developed due to stresses. This is the usual confusion for students. And hence, this is an external force. P is an external force. The correspondingly, is there an external force at node 2? No. So this happens to be 0. Is that clear? Now I have two equations and two unknowns. Just to summarize, what did we do? We discretized. We divide, or in other words, we divided this into number of elements. Then we wrote the stiffness matrix for each of these elements. We assembled them. That's what we did here. And then we wrote down boundary conditions carefully, okay, and also put down the forces that happen. One other thing before we go ahead and solve this problem is very important to note from this equation. What is it? What is that you see? Another thing that you see. You please note that at the place where we give a boundary condition, we are not specifying the force. It is not possible to specify both a boundary condition as well as a force. What does it mean? What does it mean? It means that when I fix a particular node, the force that acts on the node is decided by the system. So if I say P, it's very clear from this problem before even solving it that the reaction for P has to be taken at the place where I have fixed. So the force that is going to happen or going to be present at this place is going to be decided by the force that you give here, right? Is that clear? So I can't specify both a force as well as a boundary condition at the same point. When I specify a force at this point, the displacement at this point is decided by the system, by the stiffness matrices. And when I specify a displacement at this point, the force that is required to sustain that effect is specified again by the system, by equilibrium and so on. We will have more interpretation of this equation, okay, and how to solve them, or how to solve this equation in the next class.